The following program is brought to you by Caltech.
All right, good morning everyone, and welcome to the Caltech Space Challenge. This is our fifth lecture in the lecture series sponsored by Lockheed Martin. And this morning I have the pleasure to introduce Dr. Damon Landau, who is a mission design engineer for the Outer Planet Mission Analysis Group at JPL. And this morning he'll be talking to us about trajectory optimization. Dr. Damon Landau.
Thank you, John. Hello, everybody. I do trajectories, but I guess more a part of my job is actual. I think myself more as a mission designer than a trajectory optimizer. It just so happens that trajectories are sort of intertwined with how I actually design a mission, which makes them fun, not only because you get to sort of understand a lot of different aspects of the mission, but also because it's a hard, numerical problem. So I'm going to talk about not just optimization, but mission design for human space exploration, not just NEO exploration. I'll get into this a little bit more on the next slide. But my view of how asteroid missions fit into the grand scheme of things is that they connect us from sort of what we can do or what we hope to be able to do in a few years off to what we'd eventually like to do. I'll also give you fair warning that a lot of these slides are charts from graphs or from presentations from doing all these different missions. So there's sort of a hodgepodge, but I think I got something that flows. So here are the missions, and here are some trajectories that go along with them. Okay, so just to sort of give an idea how I think about the mission design, the thing that sort of stands out to me to how the space program is going nowadays is that the policy for what we should do is changing faster than our ability to actually make vehicles and technologies to do those things. So given that, we really need to sort of ascribe to the flexible path objective that the Augustine Committee put out. They basically said, okay, NASA's going to BS from one thing to another. They're going to shift before we're able to do anything. So we need to figure out what sort of technologies and vehicles can we make that will actually be able to be used for multiple different missions, so that when space policy does change, you don't have to start from square one again. So part of that is to look at a whole variety of missions and see how those missions actually fall out, to see what are the characteristics that we're going to sort of need for a sustained exploration program. And I think I'll get a little bit more into what that actually means technically later. However, when it comes to designing near-Earth asteroid missions, which is what you're all here for, I sort of see it more as try to look at as big a different variety of missions as you can get to, so that you can see, okay, which ones are going to be able to adapt to different missions as the space program evolves. And again, the thing that I have sort of to anchor things in my mind is that we're trying to bridge a gap from what we're able to do today and what we one day might be able to like to do. So that's sort of the caveat for everything else that I'm going to say. So the next few slides I'll get into actually trajectory design and a little bit into optimization. So here is a fun little trajectory figure that's actually done by Brent Barbie, who's at Goddard now, but I like this figure so much that I decided to steal it. You can stand on the shoulders of giants, I guess. So the simple model is, so we start off with Earth at Earth departure. So basically, in order to figure out how we're going to leave Earth, all that we need to know is a departure date, and then we also need to have an arrival date at the asteroid. So once we have these two dates, we can look up where Earth is, where the asteroid is from an ephemeris. We have the position and the time of Earth, the position and time of the asteroid, which means that we have enough to solve a Lambert problem. Lambert's theorem basically says if we know the two positions where we are, where we want to go, and the time between it, then this arc is uniquely defined. Once we have this arc where we know where we are and we know the velocity coming out. Once we know the velocity coming out, we can use energy relations with basically patched conics in order to get this departure maneuver. So instead of having to do a more involved trajectory model, we're trying to parameterize the design space with as few different few different design parameters as possible. So basically, on the return leg, we can do the same thing. We say, okay, well, we know we'll choose a time that we want to leave the asteroid. We'll choose a time that we want to arrive at Earth. So we just have 1, 2, 3, 4 design parameters. We do Lambert fits out, Lambert fits back. On the asteroid, we just follow the asteroid's orbit, and that that completely defines the trajectory in this simple model. And then once we know the velocity arriving at the asteroid, since the asteroid doesn't have any mass, the delta V is just to kill off all the relative velocity. So that's just sort of, I don't know, glossing over half a semester or so of orbit dynamics. But that's basically the model that we use to go to actually generate all of these trajectories for the interplanetary stuff, the heliocentric portion. I have my caveat here that if you want to look at proximity operations, that is, how once we're at the asteroid, how are we going to park? What are we going to do around it? That does not lend itself to a simple model. Basically, you have to start, because the force of the asteroid, the gravity is so small, it's sort of on par with what you can get from solar radiation pressure, from tidal forces, just from having an orbit that's slightly different than the asteroid. However, to make a long story short, current research says that most objects can be orbited after you check them out a little bit. And that characterization portion can happen once you arrive at the asteroid. So sort of the main reason for this in terms of how it goes into the mission is when you get to the asteroid, it might be characterized beforehand from a robotic mission, but you might want to design some time in to actually check it out a little bit more. So because we can get away with, for the interplanetary trajectories, we can get away with that simple model. That means that we can basically blast through all of the targets and figure out which ones are actually of use. So the NEO target search isn't something that I necessarily recommend for you guys to do, but I think Prakar and John came up with some papers that already sort of have filtered down some of the targets. But in case you're interested in the process of how those targets came to be, this was sort of the process that we set up, and we did this. It was a joint JPL and Goddard search that went on over the winter. The Goddard folks did the impulsive trajectories, and I did the low thrust stuff. So so in general, whenever I need to come up with trajectories for a mission, it's a two-step process. Do the broad search over as many different combinations as you can get to, and then do a filter to find the diamonds in the rough. Once you have that filter, then you can go through the optimization process, which is usually more numerically involved. So when we did this, we did it over the winter. We looked over the 7,000 some odd objects. There's probably closer to 8,000 now, and looked over launch years 2020 through 2035. And the way we did it is we discretized the design space. So we say, okay. So here showing from launch days 2015 through 2040, basically set up 7-day increments. So this is that sort of first is design variable, the launch date. The second design variable is your NEO arrival date. The third is the NEO departure date, and the fourth is your Earth return. So these are the sort of four things we saw on the slide before. And then in terms of trying to set up an actual problem, this is how I set it up. So we get all these different dates here, all these different dates here, and basically just plow through all of them with Lambert fits. So since Lambert fits are based off a conic thing, it's relatively fast. So you're able to calculate about 2 billion trajectory legs in a day if you have a decent Lambert solver. So that's basically doing all of these. And then the nice thing is about this particular setup, you see that we designed the design variables before we calculated in any of the trajectories, which means that we can decouple the outbound legs from the inbound legs, which greatly reduces the actual computation cost that you have to do. So you can calculate the inbound trajectory legs first because the inbound legs don't really depend on the outbound ones. And then in a post-process sort of exercise, that's when you say, okay, well, I want to keep everything that has a stage time greater than 30 days or whatever you guys decide should be the stage time, and I want to keep everything with a flight time below whatever I want. And again, I went up to 720 days because I'm looking for missions that will eventually lead up to Mars, and Mars missions typically take either a little bit less than 2 years or a little bit more than 2.5 years. So that's why we want to push everything up to here. However, you might decide to shorten down on this, especially I think we're hearing from the radiation guy this afternoon, so he'll tell you about why flight times pushing up past a year might be trouble. So that was the basic process we went through. Just search over everything in a big trajectory grid, filter it down to a bunch of objects, and then from there, save the top 50,000 or so for optimization. And the results of that process have been published here and there, and I think it's in a few of the resources that they put up for you. So instead of having to plow through the whole thing, part of the nice thing of the process of sort of varying over launch date, varying over the arrival date, varying over flight times is you can get sort of contour plots. So here's the contour part that the Goddard people plot that the Goddard people came up with. So this is they call the PCC plot, the pork chop contour plot, even though it doesn't really look like a pork chop anymore. But they have the launch date on the bottom versus the flight time going up the side, and the colors are the different delta V. So you see in sort of the sweet spot of the launch window, you get the low delta V missions, which will help reduce the launch mass that you actually need. But it also gives you a clue, okay, do we have a long launch window in order to do this mission? How do things vary in terms of that? And doing that type of process, again, is not that computationally intensive. So you can basically just go through a four-dimensional grid in order to get this data. And then here's a different type of plot. It's not necessarily like a contour plot. It's more like a Pareto front plot, where I have the delta V versus flight times for a few different targets here. So again, this will help when you're doing trade studies. Again, the key to getting out good designs is to try to look over as many different designs as possible and to actually understand the trade. So if the life sciences people, the life support people say, okay, no, there's no way in hell that we can keep somebody alive for 150 days, then you say, okay, well, if we're able to go a lot longer, we're able to do this, if we're able to push down, then it costs this much. And part of the idea is to actually look at these curves and try to find the knee in the curves. When do these things actually start to take a turn for the worse or the better? So if there's a trade in the flight time, say, with technology that we have now, or the Orion crew capsule, we can keep people alive for 150 days. But as you sort of go down in delta V, the propellant mass goes down, but the habitat mass might go up. And when you include the entire system, you can end up with an optimal in terms of your launch mass or your cost or something like that. So this just gives an idea of sort of how these things play into each other. Also, I was looking over a lot of references, and none of them give like specific trajectory details, or not a lot of them, where they actually give you the launch date, arrival date, and all of that. But I remember that with Nathan Strange, who I think some of you guys talked to yesterday, we made a poster with the people at the ESA's Advanced Concepts team. So basically, if you Google DPS Nathan Strange, I can give John and Prakar this poster, but it's got a shload of different asteroid targets on it with all the dates you need to actually recreate the trajectories, if you're so inclined. So a few of the other things that sort of popped out as we were doing this trajectory search in order to tweak the parameters is in a lot of the designs, when we return to Earth, we have the crew capsule, which is usually based off the Orion crew capsule design, returning into Earth and doing a direct entry into the atmosphere. However, that thing is only designed to withstand only so much heating. So we were trying to figure out, okay, well, how do we slow down the capsule before entering the atmosphere so it'll make it? And so one of the things that was first proposed is, okay, well, we know that doing maneuvers within the deep within a gravity well is very efficient for killing off energy. So we said, okay, well, if we need to change the entry speed at Earth interface from 12.5 kilometers per second to 11.5 kilometers per second, if we do it right above the atmosphere, then it's only 1 kilometer per second. However, doing a large maneuver like that right before you're going to do entry operationally is not is pretty much a no-go. So instead, we say, okay, well, you actually have to do it a little bit farther out, and because this curve is so steep at the beginning, even doing it 12 hours beforehand, which again operationally isn't that good, you've pretty much just killed off all your benefit anyway. So we sort of designed the slowdown maneuvers to happen several days before Earth interface, when we're sort of doing these simple conic trajectories. However, instead of doing it right before Earth interface for a lot of different trajectories, it's actually more delta V optimal to put in a deep space maneuver. I don't think that the software that you guys have can do these, but it might be something just to sort of take note of, that if you are stuck to sort of a simple trajectory model, then the trajectories do lend themselves to additional optimization, where you might be able to actually eke out a little bit more. So basically, instead of having to eat up a very large difference, like two and a half kilometers per second, you can get it down to, so you can lower the entry speed. Doesn't necessarily have to cost you as much in order to actually complete the mission. Another thing that they looked at for the returns is on the return duration. They're also entertaining the idea of sort of leaving the big habitat behind. So if we're looking at missions that are longer than two or 3 months, you basically have to have a larger habitat, because the Orion capsule itself is too small. But if you have a short return duration, then you could perhaps have the crew just return in the Orion capsule, so that this maneuver to depart the asteroid doesn't have to be done by the entire deep space vehicle. You can do it with just the Orion capsule and do a short return from the asteroid back to Earth. So you can do trades on the return duration as well, to sort of see how that affects the delta V. So if it turns out that this hit in delta V is totally offset by the reduction in mass by returning in a smaller vehicle, that could be a good design trade. And there are indeed architecture trades galore. This chart isn't so much to go into depth, but it's more just to, I guess, befuddle you with a whole bunch of different things you can do. One of the things, one of the key trades that I like to point out is, so on the left here, we have a bunch of different architectures based on basically how we arrive, but all these are using the Earth-Moon Lagrange inner Lagrange point as a node, whereas the ones on the right, we're using just a high Earth orbit. So we're not taking the extra time or the extra delta V to get into and out of these low energy orbits. And with the crew on board, you can't be just moseying around the Earth-Moon system. So we find that the initial mass in high Earth orbit, so in the node, so the mass to low Earth orbit, which will be your launch vehicle cost, is basically a scale up from all of these. But indeed, it can save you significant mass in terms of how much mass you actually need to launch. And when you actually do translate this into how many launches you'll need, it can save you half a launch or a big launch on one of like the Saturn class launch vehicles. So it saves you 50 to 100 tons. So yeah, I just mentioned staging a little bit. So I'm going to get off of sort of talking about trajectory optimization stuff and more into how trajectories can be worked into architecture choices and vice versa. And I think John Baker talked to you guys yesterday about architectures, and you guys heard from Brett this morning. So here's the cartoon of sort of how we're thinking about initiating the mission. So here we have our big old deep space vehicle, which years before the crew would even launch, we sort of launched this deep space vehicle. You can actually construct it in low Earth orbit, and it's not so much a construction as much as so here. So in our design, we had a SEP stage. So here's our SEP stage, which we can launch in a single vehicle. Here's the deep space habitat. Here's an extra propulsion stage. So all these can be separate launches, and you just sort of connect the blocks like how we built the space station. So once we have that sort of mini space station built in low Earth orbit, we can use the SEP stage to begin to spiral up into an elliptical high Earth orbit. So here we are with the deep space vehicle up in the elliptical high Earth orbit. When it's coming a month or two before the optimal time to depart for the mission, then the crew launches. So the crew needs to do this big maneuver to get out of low Earth orbit up to high Earth orbit. But the crew's just in this little rinky-dink thing. So the sort of gear ratio on these is much different. So it's a good way to save mass. So they rendezvous with the deep space vehicle in the elliptical orbit. And then you want to keep the orbit elliptical because you can get down, and again, when you're deep within the gravity well, changing your energy is a lot more efficient. So that's where we do our maneuver to leave and get out. So that's sort of the architecture that I've been pushing lately. So why would we do this? So basically what happens is for that gigantic vehicle, in terms of the interplanetary trajectory, the high Earth orbit staging lowers the delta V you have to do by roughly 3 kilometers per second. So if you have a whole bunch of trajectory data, you can make plots like this where each single one of these dots represents a different, a whole series of asteroid missions that occur on average once every Earth-Mars synodic period. So, and this is looking over the 2020, 2035 timeframe. So each of these represents like 7 different trajectories. And what we can see is if we only have so much delta V capability out of our propulsion system, and so these are all high thrust trajectories, then if we cut off the limit at like 6, then for if we're only able to keep people alive in space for 270 days, then we're left with only little rinky-dink asteroids. However, as our capability gets better, that is, as our propulsion systems can do more work, or as we figure out how to keep people alive in space more, then we can sort of move up from the little asteroids to more interesting asteroids, not only from a scientific, potentially from a scientific standpoint, but just from a hey, we're trying to do something cool and sell it here, and going to a 300-meter object probably sells more tickets than going to a 10-meter one. And again, whenever I talk about NEA missions, I always try to anchor it from what we can do with cislunar stuff all the way up to Mars missions. So here's the sort of conjunction class Mars missions, the ones that take a little over 2.5 years, or the shorter flight time ones. So that's why these things go all the way up. But if you guys are more interested in just sort of the very first asteroid mission, then you might want to consider things that are sort of lower in terms of flight time. But the idea is, if we start off from high Earth orbit, then it basically shifts our capability up. So things that we designed to do lunar orbit missions in the next 10 years or so, we can use that basic propulsion system for our deep space stuff, and basically raise the bar. And if we're able to keep people alive in space for a year, then we can get up to 100-meter objects instead of being limited to the objects that just come near us. So yeah, that's the gist of that. However, this delta V of 3 kilometers per second doesn't come for free, but if you have SEP, it comes for cheap in terms of mass. So here are some contours for how we'd actually spiral some of these things up. So we have, I have ISP plotted along the bottom here. So the ISP represents different propulsion systems. So usually when you hear solar electric propulsion, you think of really high ISPs, which are more like the ion thrusters, like what the Dawn spacecraft is flying. However, at lower ISPs, you can get into Hall effect thrusters. And the nice thing is, for a fixed power, so I have the power ratio on the right here. For a fixed power, the lower ISPs give you much shorter flight times. So here we have the mass ratio. So this is the mass cost. This is the time cost. And you guys can play around with this to see, okay, what sort of makes the best trade for your mission. The sort of design point that I roll with is 3,000 second ISP and about twice your power in kilowatts as your IMLEO in tons, which gives you 70% of whatever you launch up as payload. So if you have a 100-ton launch vehicle, 70 tons of that is useful payload. That's not even including the solar electric propulsion system that gets you up there. That's 70 tons is what you can send off into space. And again, at that design point, the spiral time comes up to a little bit over 2 years. And we picked that one because it's the Earth-Mars synodic period. So it helps sort of get on a cadence for eventual Mars missions. And so if you're interested in looking at this, a little bird told me that John Baker said that SEP stuff might be too complicated. But when it comes to spirals, there's a really simple sort of cheat sheet here. So I can go over this in more detail later. But basically, we have the jet power is just a function of the mass flow rate of the propellant times the exhaust velocity powers 1/2 m dot v squared. This is just the rocket equation. This is the delta V to estimate doing a long spiral. So this is actually from Edelbaum's work. So if we start off in low Earth orbit, you have the velocity in low Earth orbit. If you want to spiral up to the moon and use lunar gravity assist to get you set up on your way, you just take the difference between those velocities, get your delta V. Once you have your delta V and you know your launch mass or your payload mass, you can back out what your propellant mass is. Since we're assuming that the thrusters are on the entire time, you can pull out the mass flow rate, and the time to spiral is just your m dot divided by, or your propellant divided by the flow rate. And you'll probably want to add on some margin to take care of radiation degradation from going through the belts. And also Earth's shadow will extend the time. However, I made these plots using this, so that's sort of one way in order to get a handle of how you actually use, how you can use solar electric propulsion in the mission. And here I have some hardware rules of thumb. So yeah, we basically did all this work and saw, okay, well, electric propulsion can really buy you some decent mass benefits. It could reduce the number of launches you have to do by half, which could potentially reduce the program cost by half. But are we just BSing ourselves saying, okay, well, we have this we're assuming this technology, but does it really exist? So we talked to the technology guys, and we got John Brophy's law for how solar array power has been going. So the space station arrays, if you had them all going on all at once, would generate up to 260 kilowatts, which ends up being plenty in order to do asteroid missions. So if we want stuff that's between 200 or 300 kilowatts, it's sort of along Brophy's curve here, and there are people throughout NASA and outside of NASA that's actually looking at this technology. How do we make big solar arrays in order to generate a lot of power in space? So this is sort of how you generate the power, and then we also have big honking thrusters in the laboratory that will be able to actually process all that power in order to push the deep space vehicle around. So we have big ion thrusters, which again are the ones on the sort of higher ISP range. But we also have Hall effect thrusters where, make a long story short, you get a plasma in this torus here, and you set up a magnetic or electric field between them, and you get a Hall effect that shoots stuff out the back. And the nice thing about these, they do operate at a lower ISP, but for a fixed power, you get a higher thrust, which means for fixed flight time missions, they come in handy in order to get the job done in a reasonable amount of time. And not only that, the main thing that wears these guys out is the walls of these things erode. But because it's a plasma and you're actively working the magnetic field, you can basically design it so that it doesn't wear out as fast. So you're able to sort of reuse these types of thrusters. The solar arrays degrade sort of gracefully. So once you sort of develop a big solar electric propulsion vehicle, you can sort of reuse it over and over again, which can help with program costs and mass and all of that. So if we did want to design a vehicle, how big would it be? So this in the middle is the actually interplanetary habitat. So this is the thing that keeps the crew alive. Here's the Orion capsule, a big stage, and then here's the big SEP stage. So the big SEP stage is about as big as, I guess, old Ironsides. But to make it more believable, it's smaller than Battlestar Galactica. So in my book, let's do it. And then I guess on a more technical note, it's actually smaller than the space station. So if we can build this, I think we can build that. This will come later. So if we do have a big SEP stage, then we have found trajectories to interesting targets that we're able to do in flight times of a year or less. So in a lot of the chemical trajectory architectures, you may have heard a lot of people are saying, okay, well, there's only a handful of objects that we can get to every now and again. But if we invest in better technology, then we can get to some interesting objects. So here's one, 2008 EV5, which is it's over 400 meters across, and it's a C-type asteroid. So I don't know if Don Yeoman's talked about the different types of asteroids, but the C-types are carbonaceous, so they're thinking there might be organic material on them, which makes them scientifically interesting. So in the mid-2020s, there's two different missions to decent-sized objects that you can get to without having to launch that much mass up, and the power levels are well within that we have for the space station. If you want to go to bigger objects, or if you want to fill in different launch years, then if you have a bigger SEP stage, then you can do that. Or if you want to go with a really small SEP stage, so this is the power just for the interplanetary part. You probably want more power to do that spiral in a reasonable time. But here's one of those smaller objects that comes up a lot as something easy to get to. So the objects that are really easy to get to with chemical missions are also really easy to get to with SEP. And sometimes you may be able to actually do the mission with only one heavy lift vehicle or a couple of not so heavy lift vehicles. Again, you can push down on flight time. Pushing down to 180 days with SEP is kind of rough, but there's a bunch of ones with 270-day flight times. So here are a couple examples in the that book in the 2020s. So here's one to about a 100-meter object, and this one's to Apophis, which is also known as 2004 MN4. And the basic idea here is as you figure out which technologies are most useful for what you need later on, you can sort of back that up to, okay, what does it buy me up front? And once you sort of have that idea figured out in your head, you can say, okay, well, we'll start off with really easy missions to begin with. So here's one in the mid-2020s that this is sort of the best 180-day mission I found. So it's low power. You leave Earth, you hang out at the thing for a month, and then you come back in less than half a year. But it's only a really small object, which might not so much make the news, but you can keep going to larger objects. So here's Apophis again. This is in between that 270 and the one-year mission. So this is right after it does its infamous flyby on April 13th, 2029. But then as we go from sort of moderate powers to higher powers and higher flight times, we can get to really cool objects. So here's 1986 FG3, which is again a C-type. It's it's thought to have a lot of organics. It's a really dark object. Its albedo is like 2%, but it's almost two kilometers across, and it's a binary, which operationally makes difficulties, but in terms of science return and exploration return, I think is a really compelling object. And then as we get things that eventually might get us out to capability that we could get to Mars, then we can get to even more objects. So here's one that I think sort of more representative of what we'd want to do in order to learn how to do Mars missions, because like Mars's orbit is out here, and we're actually going out past that. But again, this is like a two-year mission. So this one's not going to be the first one, but this might fit within a progressive evolving space program. And so once you sort of understand all of these trades, and you understand the chemical trades, and you understand what NTRs do, you can get a plot like this, which again just sort of drives home the point. We want to look at which different technologies, SEP, chemical, nuclear, thermal, longer flight times, better rockets that actually can connect the dots from what we can do with cislunar stuff and can connect the dots up to things that will eventually get us to Mars. So I'll entertain any questions now.